I'm going to continue working on the report that I started in previous videos. In the last video, I looked at the full model and I decided that I probably do not want to include price in that model. Removing it will reduce from 3 to 2 explanatory variables with only a 2 percentage point reduction in the amount of variation in ice cream consumption that is accounted for by my model. Before I put the final nail in the price coffin, I'll bring to your attention a couple things. One is that in my theoretical model, when I started discussing price, I really thought that maybe it depended upon income, whether it was influential or not. And because I don't know the relative nature of these incomes, to me they all look really small. But remember that this is weekly income back in the early 50s. I don't really know how to contextualize that. But let's just suppose that these were all quote unquote high incomes. That is, for the time, they were relatively high, or conversely, they were all low income. Then in those particular cases, maybe it was the fact that price didn't make much difference. Either if they're all really low income, folk couldn't afford the ice cream, or even a better scenario is they're all high income and therefore price doesn't make much difference. So I don't have the tools yet to be able to check the way that I thought of price theoretically as it might relate to income. So I can only really look at price as it's directly influencing consumption after removing the effects of the other variables. And so let me go ahead and calculate the partial and semi-partial correlation coefficients for that. I may have done this already, but now I'm kind of formalizing everything. So forgive me if I've done this already and you've seen it already. But I just want to go ahead and make some statements to further justify removing price. So I already have the semi-partial squared, and that is that 2 percentage points, or 0.02. That's the semi-partial squared. How do I know that? Because when I reduce the model with price, that is, take price out of the model, I reduce the coefficient of determination by 0.02. So let me go ahead and get the partial. Remember, the semi-partial is how much I reduce out of the total variance. Now I'm going to get the partial, and I do think I have done that because I remember talking about we had about 30% of the variance left, 28% after we had temperature and income, or actually 30% left after temperature and income. So what does price account for of that 30%? But I forget what that number was, and I want to go ahead and put it in my report. So I'm going to go ahead and do that again. So I guess repetition's not a bad thing when we're learning. So if I am repeating, no apologies, because you're learning. So we have partial 1. We are going to go ahead and take income and temperature out of consumption. And partial 2, we're going to take income and temperature out of price. And so taking income and temperature out of price, and take some shortcuts here by copying and pasting. And then what I want to do is look at let's go ahead and go right to the partial squared. So what I want to do is get the correlation of the residuals. And I'm going to square that. And I need to reload the data because I shut down my R notebook since my last video. And let's try again. Okay, so there's a number that might look familiar to you from before. we're accounting for 6% of the remaining variance. So it is not having a lot of impact here. So I'll go ahead and add these. Let me tell what this is semi-partial of. Okay, so combining these results, I have decided to remove price from the model, providing more parsimony with little cost, little expense. A little play on words there since we're talking about price. Okay, so I'm going to go ahead and put all these up for my reference up here. So now that will give me the full model. It will give me the full model, of course. Well, let's see. I did not get the semi-partial here yet. I need to do a reduced model. So that was, see if I still have that here. I don't. So that reduced model was, we called it our income temp model. And took price out of the full model. Okay. So now when I run all this, it shouldn't show below, but it should show up here in my console window. And so I see the full model. I see price with the fairly large p-value of 0.22 indicating instability. I see that the reduction is from 0.719 to 0.7021. That gives me my semi-partial squared, and then I'm getting my partial squared of 0.06. So everything is documented here. Even though I'm not showing the output, I'm just pulling out the pieces of the output I need in order to write this paragraph. All right, so I can take this out of here, and let's continue on. So now I'm left with income and temperature, which I already know what that model looks like. So let's go ahead and see. We already looked, I think, in a previous video of what would result of taking out income or temperature. But again, since I did that before and I have very little memory power, I'm going to go ahead and put it in again. So I'm going to do an income model and a temperature model. Now I actually do know what those are going to look like in terms of R squared because those are single variable models. So my income model is going to have an R squared that's small, 0.04 squared, very, very small. My temperature model is going to be a 0.77 squared. So an income model is not going to cut it. I can tell you that right now. Temperature model, perhaps. Temperature model, if I square this, I account for 60% of the variation. It's still 10 percentage points less than when I have income in there. And if I have an income model, I account for about 0% of the variation. So why do I have a 10% drop? Why do I have a 10% drop when I take income out of the model? It must have to do with this relationship here, right here, of temperature with income. There is a correlation of the two of those. So let me go ahead and calculate the semi-partial and partial squared. Actually, I know the semi-partial squared for income. The semi-partial squared is that I am going to reduce from a model that includes, what was it back here? Let's see again. It was the model with just income and temperature. Here it is. 0.70. 0.70. If I go to, if I take out temperature, it will go all the way down to almost 0.0. But what I want to know is the semi-partial with income. So, and I know that from squaring the temperature, but that's getting a little bit messy. Let me go ahead and actually just put these models in there. So I have an income model. And I have a temperature model. Okay. So I was focusing on looking at income and wanting to know why, even though income had such a small correlation with consumption, almost zero, that accounted for almost 0% of the variation. Why, when we had that, almost zero correlation and almost 0% or zero coefficient determination, why did we end up losing 10 percentage points when we drop it from the model with temperature in it? So the semi-partial for income would be, the semi-partial for income I can obtain by comparing the model that we had with ice cream and income both, I'm sorry, temperature and income both, on ice cream consumption. I've got ice cream on the brain. 0.7021, how much do we end up contributing to the model above and beyond temperature? So we had a 0.7021 here, and for temperature, we had that one down here. For temperature, it was 0.6016. So 0.7021 minus 0.6016 tells us how much we add. So we add 0.10. That's our semi-partial. So the semi-partial squared, let me go ahead and start making notes about this. Okay, so I need to calculate the squared partial now. So let me go ahead and do that. I'll call it partial 3, not to be confused with the partial 1 and partial 2 up here. So what I want to do is remove temperature from ice cream. ice cream consumption, that is. And I want to remove it from income. And I want to get, I called both of these partial 3s. We need one partial 4. I want to look at the leftovers after we remove temperature, everything else. And I'll do it squared. And this gives us a partial squared of 0.25. So that means that we're accounting for a full quarter of the remaining variation. And so if you remember seeing this from an earlier video, it's because I used this as a suppression example, that the inclusion of temperature in the model was suppressing the impact of income on ice cream consumption. So what this suggests to me is that even though I had a very small zero-order correlation of income with consumption, when I have temperature in the model, we get a much better effect of income, and therefore I am not going to want to take it out of my model. At least that's my choice. Even though temperature would be a nice parsimonious model, simply one variable, I don't want to reduce by 10 percentage points. And the fact that I have this partial squared of 0.25, if I take the square root of that, my correlation that I can compare to my zero-order correlation is 0.50. So you compare 0.50 to 0.05. And that comparison of 0.50 to 0.05, one is with temperature, without temperature in there, and one is with temperature in there. So if we account for temperature, so this 0.05 up here, this 0.05 that we got in the model here, that is the correlation of consumption and income, ignoring everything else. So that means that if temperature is related to income, it's in there. But then once we take it out, temperature out, then we get that partial squared of 0.25 or that partial of 0.50. So let me go ahead and talk about this. The square of the partial for income after accounting for temperature is 0.25. These are large enough that I want to retain income in the model. I have already seen that temperature is the largest single predictor, so I am keeping that in the model as well. All right, so I've basically settled on a model now, and I'll go ahead and hide all this. And so now that I've settled on a model, the next thing to do is to start talking about that, what that model means. And then once we've done that, we can turn our attention to inference. So we'll continue on doing that.